Good afternoon, everyone. I welcome all viewers to the 29th Vyakyan in the PRL ka Amrit Vyakyan series of the online lectures or Vyakyans. This series of 75 Vyakyans began on 4th of August last year and is being organized every Wednesday at 4 p.m. to celebrate the Platinum Jubilee of Foundation of PRL. The Vyakyans are delivered by eminent speakers from India and abroad from diverse fields of science, engineering, management, etc. Starting last Wednesday, the 9th of February, until mid of March, the PRL Ka Amrit Vyakyan Committee has planned to host lectures by distinguished women speakers to celebrate the International Day for Girls and Women in Science and International Women's Day, and to honor and recognize the outstanding contributions of women not only in science but other fields as well. Today, we are honored to have a very distinguished speaker for the Amrit Vyakyan, Dr. Lalitambika, distinguished scientist and former director of the Directorate of Human Space Program at ISRO. In fact, she was the first director of the Directorate of Human Space Program. On behalf of the Director PRL, my colleagues, and also on behalf of the Amrit Vyakyan Committee of PRL, I extend a very warm welcome to Dr. Lalitambika. Thanks for gracing our celebrations at PRL at 75. I would now like to invite Director PRL Dr. Anil Bharadwaj to introduce the speaker to the audience and to request her to deliver the 29th Vyakyan in the Amrit Vyakyan Mala. Over to you, Dr. Bharadwaj.
Thank you, Dr. Nandita. Namaskar, Kencho, Adabaz, good afternoon to all the viewers and listeners of the 29th PRL Ka Amrit Vyakyan. It is my privilege to introduce my very good friend and great colleague, Dr. V.R. Lalitambika, who is the Vyakyan Karta for today. We had a very long association in Vikram Sarabhai Space Center and has also shared very light moments while traveling to the cars. Well, Lalitambika is a well-known figure in ISRO and aerospace fraternity. But for the sake of viewers and listeners for PRL Ka Amrit Vyakyan, let me formally introduce Dr. Lalitambika. She graduated in electrical engineering in 1984 and followed on to did her master's in control engineering from College of Engineering, Trivandrum. After a brief stint of teaching at NIT Kozhikode, she joined Vikram Sarabhai Space Center in 1998. She grew ranks at VSSC and was the deputy director of the center, looking after the control guidance, design, mission, simulation, analysis activities, before moving on to Bangalore in ISRO headquarters and becoming the first director of the Directorate of Human Space Program. She has played a nodal role in defining the goals and targets and policy shaping the Indian Human Space Program, which includes crew selection and training and technical systems for finalization of Gaganyaan, establishment of Human Space Flight Center, and synergizing the national efforts in this direction. She has been the chair of many committees with respect to our interactions with various space agencies, representing India on those committees, and has been in the forefront of the Gaganyaan mission. Dr. Lalitambika has been honored with several awards. A couple of them I will just mention over here, like Indian National Academy of Engineering Woman Engineer of the Year Award in 2020, ISRO Performance Excellence Award in 2013, ISRO Merit Award in 2010, Aeronautical Society of India Space Gold Medal in 2001, which she got from the hands of our former President of India, Dr. Abdul Kalam. In addition to that, many other recognitions are there. A couple of them I will just mention over here, like Woman Achiever in Aerospace 2019, Marie Curie Mahila Vijnana Puraskara by Swadesh Vijnana Andolana 2018. And she has got honorary doctorate or DSc degree from Satyabhama University in 2017. She is also a fellow of Indian National Academy of Engineering and is currently also a governing council member of Academy. She is also a member of Aeronautical Society of India, Astronautical Society of India, System Society of India. And she is a core aerospace scientist with specializations and interest in aerospace mission, navigation, guidance, control, simulation. She has guided several MTech and PhD students and has more than 60 refereed publications to her credit. Lalitambika as the word, it means goddess Durga. And another word which I was just searching around is the person who is easily approachable, and within quotes, mother. And now she is a grandmother. And this I can say for sure that she is easily approachable for two reasons, because we had a long association in terms of traveling together in the official car while going to VSSC. And when I requested her on WhatsApp to be our Vyakhyan Karta for PRL Kamrit Vyakhyan, she readily agreed. So with this few words, I will request my colleague and friend, Lalitambika, to deliver the 29th PRL Vyakhyan. Over to you, Dr. Lalitambika.
Thank you so much, Dr. Bharadwaj, for that wonderful introduction. Good afternoon to you all. It is my privilege to join the PRL Ka Amrit Vyakhyan lecture series. And I thank Director PRL and the team behind this lecture series for giving me this opportunity. These are very exciting times for the space community. There is a renewed interest the world over in crewed space exploration. And this is a technology which we in India are also now striving to master. And it will hold the key to our ability to contribute meaningfully to all the future international ventures. And this also is the theme of my talk. So I am thinking of taking you through the major challenges of crewed space exploration and the strategies to overcome those challenges. And I'll definitely touch upon our own program as well as we go along. So now I'll just share my screen. Okay. So I hope it is visible everywhere.
Yes, perfect. Please go ahead.
Yes. So the drivers for space exploration have conventionally been twofold. One has been space science and the other has been human spaceflight. So during the Cold War era, the scenario was actually one of competition between the superpowers. So there was this race to put the first man in space and to reach the moon first. And this race had far reaching consequences for the development of technology. Not just the race, it was also the very ambitious timelines which were set by both the US and the USSR. What happened was technology development was spurred to such an extent that there were such a large number of developments within such a short period of time. But then later on, once the race was over, the benefits of mutual cooperation were realized. And all countries realized this. And cooperative scientific research has been happening over the past several decades in low Earth orbit. Basically in the International Space Station and in the Mir also before that. And now also it is continuing. This has been yielding important benefits for humanity. So if we are looking at the history of space exploration, from the first satellite around Earth in 1957, uncrewed exploration has come a very long way. We have put rovers on Moon and Mars. We have explored both the inner and the outer solar system and are investigating the sun as well, and have even gone beyond the solar system and are navigating interstellar space, as we all know, with the Pioneer missions, the Voyager missions, etc. But at the same time, the crewed space exploration has never totally left the vicinity of the Earth. It has at most ventured to the moon. Of course, we are thinking of going to Mars now, but we have to see when it will actually happen. So there is this vast difference that exists between the ground that is covered by uncrewed and crewed spaceflight. So there are two challenges are actually twofold, and one is human related and the other is engineering challenges. And there's also one more aspect to this. In a human space mission, the main focus of the engineering system designer as well as the medical professionals is on the safety and well-being of the space travelers and not on the performance as in a regular mission or what we call a robotic mission. So now this is actually not India's first experience in human spaceflight. As we all know, India's first experience of human spaceflight came when we collaborated with Russia, the then USSR, for the mission to Salyut 7, wherein our first astronaut, Sri Rakesh Sharma, he flew and he in fact carried with him the ambition of millions of Indians. So this particular experience, it gave not just the experience of space flight. We gained a lot in terms of technical experiences in the field of astronaut selection and training. Of course, they were very preliminary, but we did gain something which we never knew at all before: microgravity experimentation, payload design, then space medicine, space food, in all these. And there were also tremendous intangible benefits, such as inspiring our youth. And in fact, this had given an inspiration to the space program as well, space exploration. It inspired it, space exploration. And of course, the strengthening of the international relations with other spacefaring nations. And the Indian space program already has extensive experience with conventional spacecraft, also has a successful record of frugal engineering. And we do have a launch vehicle, that is the GSLV Mark III, which can loft comparatively heavy payloads into low Earth orbit. So that is where we are now. So I have summarized the areas where major technology challenges exist for space exploration in this slide. And many of these challenges are actually interrelated. For example, propulsion and materials, they play a major role in the transportation technology limitations. So I will be explaining this in detail in the next slide. And then there are also space hazards, such as space radiation. There's a possibility of hypervelocity debris impacts. And it goes without saying that extremely high reliability is needed for space missions because there's no repair or maintenance option. And all these challenges acquire an additional complexity when humans are involved. So I will come back to the space transportation challenges when humans are there. When humans are involved, in addition to the elements which I've just shown, there are additional requirements. Like we need to have environmental control. We need to have human-centric products. There'll be seats, there'll be health monitoring devices, there'll be medical kits. Then we'll need to carry air, water, food, etc. And in addition, we need to have an escape provision as well in case of any malfunction during the launch. So all these areas will be covered a little later. What I wanted to emphasize now is that because of all these requirements, the mass that is to be carried for a crewed mission is much higher than for an uncrewed mission. So human spaceflight translates to high payload weight and high payload volume. The mass that is to be taken to orbit actually depends on how many people we are going to carry, and what is the duration of the mission, and what is the profile of the mission. For example, I'm sure that this picture here is very easily recognizable. It's the Saturn V standing on the launch pad. It needed to take 3 men to the moon and to bring them back. And the mission duration was a week. And there was also additionally the lunar module to land on the moon. And then there was also a return mission because everybody had to be brought back to Earth. And so, how big was this rocket? So, this rocket has so far been the largest rocket which was ever built, and it is only now overtaken by Starship of SpaceX. It's 9 meter taller. And so, why do launch vehicles have to be so large? So that gets explained in the pie chart which is here. That is because of the very limited payload capability. You can see that in this pie chart, the proportion of payload is less than 1%. These numbers are all representative, not exact, but it is all of this order. So why is this so? We can see that the maximum portion is the propellant weight. That's because we have to carry both the fuel and the oxidizer, unlike in a aircraft. And then there is the encasing structure. So this leaves hardly 1% of the liftoff mass for the payload. So what it means is that if you have a 500-ton launch vehicle at liftoff, you get hardly 5 ton as the payload mass. Even that is a very good figure as far as the rocket engineering is concerned. And that is the useful mass in orbit. So it is necessary to have technological breakthroughs in propulsion and materials, if we have to overcome this limitation. Why? How will this help us? High specific impulse propellants will deliver more energy per kilogram of propellant. So that will lead to lower propellant mass. So the proportion of propellant in the pie chart comes down. And if we have air breathing technology, we no longer need to carry the oxidizer for the atmospheric phase of mission at least. So then it will again come down. Once we develop low weight and high strength materials, and also have a paradigm shift in structures from the current kind of static, stiff, and heavy structures to adaptive, lightweight, and versatile structures, the share of useful payload will increase dramatically. Now, this is something which is really required if we need to have big missions to Mars and beyond. So, that is one of the factors that has been preventing us from going beyond the moon. And when we consider interplanetary missions, and I'm coming back to the propulsion technology here, chemical rockets they are actually too slow if you want to go to the asteroid belt and beyond, because you will need more than 5 years just to reach the moons of Jupiter. In a human lifespan, that is a huge time. It's not just time, there are many other challenges, psychological challenges, and also resource related challenges that would be involved. And in the future, plasma rockets would be promising candidates for solar system exploration. They can shorten travel time from to Mars from months to weeks, and they can also reduce the in-space fuel usage by 90%. So we have to just see how the technology is going to unfold in the future to make large-scale human travel possible. But in the meantime, the only options which are currently available are bigger and bigger rockets. And if that is not an option, we need to extract the maximum juice out of whatever rockets are available. So, how can this be done? This can be done with optimal subsystem design and good mission planning. And for large structures like space stations, as we already know, the only option right now is to have assembly in orbit, carry up the pieces and assemble them there. So I'm just showing here one or two examples of good mission planning, which have enabled us to have good interplanetary missions with modest rockets. So as we all know, the Polar Satellite Launch Vehicle of which we have had a very recent launch also, has been used. It was originally designed for missions around Earth, but it has been used for successful missions both to Mars and to the Moon. And this was possible only because of what I was mentioning earlier, the optimal design of all the systems and optimal mission planning. And in the far future, when planetary travel becomes commonplace, I'm sure that there's going to be this in situ resource mining and 3D printing of spare parts. All that is going to also become very common. So all this will in turn reduce the mass which we need to carry from Earth. So now I'll come to the human space mission. A conventional space mission would naturally aim to maximize the performance. However, in a human space mission, the main consideration is to maximize human safety. So where do we have to concentrate? The most critical phases of a mission, I'm just now talking about the mission point of view. From the astronaut safety point of view, this would be the launch and the re-entry. So coming to the launch part, the ascent trajectory has to ensure that we can abort safely from any point in case there's a requirement. What does this mean? If your capsule is designed to land only in water, then the ascent trajectory should not have any part where an abort would result in a land on a land rather than water. That is one of the considerations. There are many others. This is just an example. And also the shape of the trajectory also has to ensure that there's a human inside, and the parameters should not be beyond the human's tolerable limit, like the accelerations and the other parameters which the human body is sensitive to. So that is with respect to the launch part. And during return from orbit, we know that there's a very high energy that is already there in the system because it is in orbit. And this high energy has to be safely dissipated in the atmosphere. So as we re-enter the atmosphere, both the thermal loads and the structural loads will start increasing. And at high altitudes, the main consideration is the heat flux. So there's a very narrow entry corridor. And this, we need to make sure that we re-enter at the right angle of attack. And as we come down further, there are specific conditions to be met for parachute deployment, which will in turn ensure a soft touchdown or a splashdown, depending on the mission design, so that the astronauts are not injured in any way. Then, of course, they have to be safely recovered as soon as possible. So there have to be recovery assets which are positioned appropriately to enable this. So all these are additional challenges. And the space transportation systems which are meant for human spaceflight are human rated. So what this means is that the factor of safety of the structures, the tanks, and all the other systems are enhanced to meet the human rating standards. So this could often be achieved by derating a heritage system, because we don't want to lose the heritage, but we derate the system so that it would be operating at a lower operating condition than it is actually capable of. And both the trajectory shaping, which I had already mentioned, and the human rating, they enhance human safety at the cost of performance. For instance, if you have a launch vehicle that could deliver 10 ton into low Earth orbit, this same launch vehicle, after human rating and after the appropriate design and also inclusion of the safe abort capability, may be able to deliver only 7 ton to 8 ton for a human space mission. The rest would be lost because there's a trade-off, because we are trying to maximize the safety. And for all the critical elements, there would be redundancies that are built in, including even the pyros, the parachutes, everywhere there will be redundancies. Enhanced robustness and fault tolerant features are built into the design of the onboard avionics and the autonomous flight control systems. They'll be at all levels, like sensor level redundancy, system level redundancy, software error recovery features. All these would be a part of a human space mission. And in addition to all this, the humans who are inside, they are also given certain freedom to act. under certain conditions as a contingency measurement. It's called human intervention capability. So, in spite of all this, even though we have enhanced the robustness of the system, it is mandatory to provide a safe abort capability so that the crew can be taken away quickly from a malfunctioning launch vehicle using a highly reliable crew escape system. And with this aspect, I am going to cover separately because it's another very important aspect. So I am showing here the abort strategy. The human spaceflight missions require reliable escape provisions, as I was already mentioning, for the crew. Mainly, this would be during the launch pad when they are in and they are strapped and the launch vehicle is yet to take off. And then during the ascent phase of vehicle launch, because that is the phase when you are having the very fast, mostly solid motors providing the boost trajectory, and it is necessary that we may not have any option of shutting down the motor. We only have to pull away the crew and the module away from the malfunctioning launch vehicle. So how can this be achieved? That's what is covered in this slide. There has to be obviously a health monitoring system which will give an extensive health monitoring of all the critical engineering and the crew related parameters all throughout. So, in case of any anomaly, it would provide the crewed spacecraft sufficient advance warning. This advance warning is required not just to safely abort, in case there are procedures which we need to follow on the launch vehicle before the abort is effected, that also has to be done within this time frame, because the crew have to be they have to be safe. The danger to the crew is to be minimized from the launch vehicle side as well. So this escape strategy would be needed to initiate the mission abort and to rescue the crew in a variety of situations. So these would include launch vehicle deviations or malfunctions, orbital module malfunctions, crew emergencies, and ground system emergencies if it is yet to take off. So the prime objective of any crew escape system is to take the crew module to a safe distance from the launch vehicle. And this philosophy of abort generally involves categorizing the time critical and the non-time critical events. And the action would naturally be based on the time available for initiating the escape. And the initiating authority also would depend on the situation, whether it is autonomous, whether it is from ground, whether it is through the crew. So, and this system, the system which initiates the abort, should naturally tolerate multiple failures. And there are a variety of parameters which are monitored, the critical parameters. I'll just give you a few, like the power, the tank pressures, the turbopump temperatures, the body rates, the separation events, whether they have occurred or not, all these. And there are both solid motor based abort systems and liquid motor based abort systems. I have given a variety of them here, including our own. And ours is a solid motor based system. So this is the successful pad abort test, which is shown at the extreme right of this slide. So now I will come to some of the other aspects of space flight, like the space hazards. There are several hazards which are associated with space flight. One is radiation. So radiation poses a risk to human health and adversely affects the human immune systems. So this cannot be avoided totally. Astronauts cannot avoid cumulative radiation exposure, which can cause cell damage. It can also affect biological fluids and may cause metabolic disorders. And there are, in fact, three kinds of radiation, as I'm sure all in PRL are very well aware. But since general audience is also there, I'll just briefly touch upon this. There could be particles which are trapped in the Earth's magnetic field. There could be particles which are shot out into space during solar flares, like particle events. And there are galactic cosmic rays which come from outside our solar system. So, how does this affect the astronauts and our missions? So, the Earth's magnetosphere is there in the vicinity of the Earth that deflects most of the solar particles, and the atmosphere also quells most of the particles which manage to get through. So, what this means is that if you have a space station in low Earth orbit, like the International Space Station, it is more or less within the Earth's protection. Our own mission is also planned in a similar orbit. But when we think into the future, like beyond low Earth orbit, their space radiation may place astronauts at significant risk for radiation sickness and also increased lifetime risk for cancer, central nervous system effects, and degenerative diseases. And solar flares, they occasionally release massive amounts of energy into space and can have serious consequences to astronauts and the equipment also, even at locations which are far away from the sun. And we have all read such an event recently in the news where several of SpaceX internet satellites, this Starlink satellites, have been damaged by a minor solar storm event. So this is something to be taken care of. And galactic cosmic radiation is a very dominant source of radiation, and that also has to be dealt with aboard our current spacecraft and also the future space missions. I'm sorry, I just now noticed that the slide has changed. Okay. So, and these can actually pass through a spacecraft, they can pass through the skin of the astronaut as well. So, in the case of short duration missions, exposure to low intensity radiation may not be much of a concern. We only have to cater to intense and energetic solar events. But for longer missions, especially beyond low Earth orbit, this danger of highly energetic galactic cosmic rays is present. So, space weather prediction and monitoring becomes very important in this regard. So, this will help us to time short duration missions to avoid such events. It will also provide sufficient advance warning to the astronauts to take shelter for long duration missions, because there has to be some provision within their capsule for long duration missions where they can shelter. So there's the other threat is something which is widely spoken about now. That is the space debris, and there are currently more than 28,000 debris objects in Earth orbit which are big enough to damage or destroy a functioning satellite. Of course, there are many more objects, but these are the big ones, and their orbital velocities are very high. So even a small chip of paint can damage. So this possibility of a hypervelocity impact collision with an orbital debris is a very real threat, and it's also a concern during launch because the launch vehicle itself will be passing through this debris field. So the launch window is usually fixed to avoid hitting any debris in the path. Because this is possible because all the large pieces are catalogued and their paths are known. And once you are in orbit, if you are in Earth orbit, then what is done is commanded maneuvering to avoid the danger. And we know that this is very wasteful of the propellant, because we mostly have to use the propellant to maneuver the spacecraft to take it out of the path. Now this is going to become a big problem because there are more and more constellations of satellites that are being launched. So we will need to automate collision avoidance, and artificial intelligence will be a major tool in this regard, not just for space hazards, to make sure that we are able to operate, network, coordinate, and protect all our space infrastructure. Now, beyond Earth orbit, the threat of orbital debris is substantially lower, but the danger of micrometeorites is unquantified. Though the danger lies that it is mostly unquantified, so it may pose a risk for long distance missions. Okay, now I will come to some specific requirements, human centric requirements. These requirements are there only because the human is there. Like for short missions, like our own Gaganyaan mission, we can carry along everything we need for near Earth like environment during space travel. We can carry our air, water, food, everything to last the duration of the mission. But for long duration mission, this is not possible. And that is why the space stations around Earth are having regular resupply missions. And we are all aware that we breathe, then we generate sweat, we generate other waste products. So inside the cabin, this can vitiate the atmosphere. So it is essential to have a system which enables humans to survive and function effectively for a long duration in space. So, this is the life support system that provides and controls the atmospheric pressure close to sea level, where we are very comfortable, revitalizes the air by removing the carbon dioxide and also the trace contaminants, and also generates oxygen. For a long duration mission, such as on the space stations, it is required to have a water recovery system. Water is a very precious resource, so we cannot simply throw it away. It is needed to collect, process, and make available for reuse all the water that is produced and used by the crew, including grey water and condensation from the air. And oxygen is usually produced by electrolyzing the water from the water recovery system, and you get oxygen as a hydrogen as a byproduct, and that in turn can be combined with carbon dioxide which we breathe out to get water. So you get both oxygen and water, and the byproducts like methane are usually vented out. So such a system is essential for us also when we move into the sustained phase of our own human space program, and research has already started into this aspect. And it's also necessary to maintain a steady air temperature, control the moisture for maintaining the crew comfort. So when resupply is not required, is not possible, as in a long duration mission beyond Earth, then we will also have to think of fully regenerative, self-sustainable life support systems. Now, for planetary exploration and for extravehicular activities, we also will need portable life support systems, which can be totally carried with us. Now, I also would like to touch upon another area where significant advances are happening in microgravity environment, and this is the space agriculture, which is going to be a necessity in the future. The challenges being overcome are multifold, like hydroponics in high microgravity environment. There's no natural sunlight and seasonal cues for plant growth, and this is still being overcome. It's a very exciting field of study right now, and the spin-off potentialities of these systems are also extremely high, because if you're looking at the life support system, obviously for medical purposes, whatever advances come in the life support system, that will reflect on Earth also. Zero waste sustainable societies on Earth and on other planetary surfaces as well in the future. Arid areas cultivation from the lessons learned from space agriculture. So all this is going to be there. It's already there in a small way. And a space suit is something which we all think of first when we talk about space flight. This is also actually part of the life support system. So, in addition to the basic pressure garment, there are a number of other equipment systems. This will include environment controls to keep the wearer comfortable, special joint mechanisms to minimize forces needed to bend limbs. There are two kinds: intravehicular activity suits would be worn inside the spacecraft, and EVA suits are different. They are much more rugged, and they need to maintain stable internal pressure, and they have to provide breathable oxygen, eliminate carbon dioxide, permit mobility, regulate temperature, and they also include a communication systems. They collect and contain solid and liquid bodily waste as well. So we can see that the spacesuits are really mini spacecraft. And you can see here at the right one one picture I've given here. You can see that their posture is different from Earth. They are in the microgravity environment. When they are in orbit, their neutral body posture and the visual aspects, the operational and cognitive aspects are all different from those on the Earth, that is in 1G environment. So the head comes down, the natural gaze gets inclined down below the horizontal, the resting position of the hands comes up, the knees are flexed, and if they need to adopt any other posture, this will require muscular effort, which is wasteful. So the gaze and the posture and other aspects, they do affect the way the astronauts sleep, relax, and perform tasks. So considering ergonomics, fully in the design process of the spacecraft is of great significance to ensure the personal safety and comfort, shorten the task time, and to reduce the astronaut cognitive load. This has to be fully considered, because it's not at all the way things have to be designed to work on the Earth. So this is something also which we are learning now. And in microgravity, this has been well talked about, but I will still touch upon it for completeness sake. Bone loss occurs, and this is a huge percentage, like 1 to 1.5 percentage per month. So this will lead to acceleration of age-related changes similar to osteoporosis, and prolonged exposure to weightlessness also increases the risk of kidney stones and bone fractures, both of which are associated with bone demineralization. And there's an impact on the muscles as well of long duration stay in space. There's a loss in the muscle mass, strength, and endurance, and this happens especially in the lower extremities. So this will place astronauts at risk of fatigue and injury. And the heart, as we all know, is a unique muscle, and there's a possibility of diminished cardiac function and the possible occurrence of heart rhythm disturbances. They are serious concerns during long duration space flight. And we would have seen that the face is puffy, the body fluids get distributed away from the extremities, there's a puffiness of the face, also changes in the cardiovascular physiology. So all this is something which we need to account for and take care right in the beginning. And we have all seen videos where they are coming back and then there's some disorientation. There is a decreased neuromuscular coordination when they are returning, and they are just taken out of the capsule and they try to walk for some time. So there may be problems in standing up, and there is circadian rhythms get disrupted because there's no 24-hour day-night cycle. So sleep loss, stress related to workload, and psychosocial factors all affect the body on long duration missions. So it is something which is very glamorous, but it is also something which is very taxing on the human system. And this loss of blood volume and some transient post-flight anemia can happen, even though they are taking a balanced diet. So these complex physiological and psychological changes will vary with the length of the mission. So this is why astronauts and crew are carefully selected, trained, and monitored to minimize risks and to promote their health and safety. And in-flight medical care capabilities and countermeasure protocols are all very carefully worked out, as well as post-flight rehabilitation. And during prolonged missions, exercise is very effective at minimizing muscle atrophy, and medications are effective in treating space motion sickness and also orthostatic hypotension. And some are also useful in reducing bone loss. So researchers continue to look for new ways to counteract the physical changes which are associated with long-term spaceflight through diet, through exercise, through medication, and a combination of other strategies. So you may have noticed that I have spent a lot of time talking about the effects on the human body. This is the main difference between a robotic mission and a human mission. The entire focus is on the human. Everything is around him or her. Okay. So now I'll come to another aspect of a human space program, the readiness of the human element of the mission. That is, the readiness of the crew and the readiness of the supporting ground staff is equally important, because only with all this can we ensure the success of the mission, in addition to the technological system readiness. So this requires a clear understanding of the crew tasks and the mission duties, as well as the ground support team's roles and responsibilities. So there needs to be a seamless coordination between the ground and the crew to ensure the success of the mission. So, in addition to extensive simulations for various scenarios, like the probable scenarios as well as the worst case scenarios, in addition to all this, the crew is also prepared for contingencies where communication with the ground team may not be possible. And I've also touched upon the major focus areas for the readiness of the crew and the ground systems in this slide. So there needs to be an in-depth operational training of the technical systems, there needs to be extensive practice sessions in ground simulators for a variety of scenarios. They need to be familiar with the documentation and the protocols related to the onboard kits. This includes the medical kits and the survival kits which they are going to deal with on board, and not just the crew, but the people who support them on the ground. They have to be prepared for nominal and off nominal landing scenarios through recovery and survival training, and the maintenance of human performance in a space mission through physical training and space medicine intervention. And the proficiency of both the crew and the ground staff have to be maintained throughout, because a mission may be, the actual mission may be of short duration, but the preparation for the mission may take a long time, and the same crew will probably have to be there for subsequent missions as well. So whatever they have gained, they should not lose, they have to maintain it. This is another very important part of a human space mission. Now I will come to our own human space program. So as all of us in India are very well aware, the Honorable Prime Minister of India, during his Independence Day speech in 2018, he announced India's human spaceflight program. And the first milestone in this program is the Gaganyaan. And this actually envisages the demonstration of human spaceflight capability to low Earth orbit. So as I already mentioned, now we have a capable launch vehicle for a human mission. And this is the GSLV Mark III, but not the regular GSLV Mark III. It is a human rated vehicle. There is a crew escape system at the top here. And there's an orbital module which consists of the crew module and also a service module. The crew module is the crew's living and working space, and propulsion and power are provided by the service module, which carries the solar panels and the thrusters. And the orbit chosen for the initial mission of Gaganyaan is approximately 400 kilometers circular orbit. This is similar to the International Space Station, as I had already mentioned. Now, I will also take you through the mission profile. We have two solid strap-ons. We have a liquid engine. We have a cryogenic engine. And then on top of that, we have the crew escape system sitting here. And we have the inside, which is not visible, we have the orbital module. So what happens is, initially, we have to carry this heavy launch vehicle through the atmosphere. And this job is done by the two heavy solid motors which are sitting here. So they are ignited first, and they provide sufficient energy to take the orbital module up through the atmosphere. And the crew escape system is actually meant for this phase. In case of any anomaly during this phase, the quick acting motors of the crew escape system will take the crew safely away, and they will splash down into the ocean and be recovered. Now, normally that should not happen. That's only a contingency measure. So as we go beyond, then the liquid engines are fired and the solid boosters are separated. And the crew escape system is also thrown off since it is not used beyond the atmospheric phase. Later on, the liquid engines are also shut down and they are separated once their job is done. And then the cryogenic stage takes over. And this is the one that actually takes the module to the orbital velocity. So once orbital velocity is achieved, then the ascent vehicle is separated, and then the solar panels of the service module are deployed to give the energy, and the service module also propels the orbital module into its final orbit. And then it continues in orbit, and then at the end of the orbital phase, the service module again comes into the picture. It deboosts the orbital module by providing the thrust in the appropriate direction to reduce the orbital velocity. So the whole thing starts coming down, and the time at which the deboost happens is also very important, because we will have some preferred recovery site. So if we deboost at the appropriate time, then we will be able to bring it to the place where we want the recovery to happen. Then later on, everything starts coming down, and well before we get into the atmosphere, the service module is separated off, and then the crew module is properly oriented so that the entry is at the right angle of attack I was mentioning earlier. and then it continues into the atmosphere. And once we are well into the atmosphere, the atmospheric drag will slow down the module, and then later on we will be deploying a series of parachutes at the appropriate altitude. So the velocity gets further reduced, and finally splashdown is at near zero velocity. So all this will not happen just like that. So there will be a series of tests for qualifying all the systems before we have the crewed mission. So this will include near flight environmental test of the crew escape system and the parachutes, extensive ground simulation of the avionics and the life support systems, and uncrewed missions to validate all the aspects before the actual crewed mission. So now I have taken you through the mission profile. So I have my last slide here. So there are a large number of technologies which need to be developed for enabling human spaceflight. So these would include the re-entry body shaping, the thermal protection system, the deceleration system, crew escape system, abort philosophy, human rating, crew selection and training, then space medicine, where the country doesn't have right now. Now only we are developing life support system and green propulsion for the crew. Now we are in a somewhat good shape with respect to some of these because we have the experience of the successful space capsule recovery experiment which happened in 2007, and also the CARE mission, that is a crew module re-entry experiment, which happened in 2018, where atmospheric entry and recovery have been successfully demonstrated. And now Gaganyaan is a national mission. It is really not just an ISRO mission. So it's the academia, the industry, and the national institutions all join hands along with the Indian Space Research Organization to achieve the mission. And once this first step is achieved, we will be in a position to embark upon sustained human presence in low Earth orbit. And I'm really looking forward to the time when that happens. Thank you very much. So I have reached the end of my presentation, so I can take any questions. I'll stop sharing now.
Thank you very much, madam.
Yes.
For taking us onto a pre-journey, I would say, into the human space program, right from the current scenarios to the plasma rockets. And you have elucidated as the challenges involved and the focus areas which one need to do and some elements of Gaganyaan. Thank you very much, madam. We have participants joined both on WebEx and YouTube panel. So we'll first take questions from our WebEx panel. So those who have the questions on WebEx panel may raise their hand, which will be taken. So we have a question from our director, sir, Dr. Anil Bhardwaj. Sir, please, sir.
Thank you, Dr. Lalitambika, for a very excellent talk, summarizing what kind of challenges are there and how we cope up with them, what kind of strategies we have to have. And being a human mission, it becomes human-centric requirements, which are enormous, not pre-launch, but post-launch also. And particularly in the health effects, the physiological effects on the crew itself. My question to you is quite novel in the sense of nuances, because I'm not directly into this area. But so far, with respect to astronauts who have gone to space, what is the kind of most difficult phase they have during the ascent and during the ascent? Total life of a rocket taking off to landing.
Right.
According to them, I don't know, because maybe you are more experienced than any one of us than this. So what is the most difficult phase they feel, is what we are trying to understand.
Very interesting question.
And number two is with respect to their own, physical health, which is the most important thing they have to take care, which they are sure is going to impact.
Okay. Thank you. Thank you for both the very interesting questions. I'll try to answer them because I have had the opportunity to speak to many who have gone. Okay. So what they say is the first is at liftoff. At liftoff, there's a huge vibration and noise. So in the simulators also, we really need to duplicate all that so that it doesn't come as a surprise. So in the earlier missions where the simulators were not really 1:1, this had come as a surprise. They were not worried because these are very unique people, you know. They are people who are very adventurous. They are enjoying taking risks, so there's no worry involved. But it was a little uncomfortable. And then the staging events. So when the staging happens, then there's a vibration. So they will sometimes not be able to see the screen. They are always looking at the parameters, even though they are not intervening. They are watching all throughout. So there could be some shock which is felt during staging. And the other one is, of course, something which is very interesting, which they see, like when they are coming back. When they are coming back, the first thing is the heating effect. So they'll see the plasma enveloping their capsule outside the sheet of flame. So that is something which they are all prepared for it. You know, they're watching out for it and they really enjoy it. And then there'll be jerk when the parachute gets deployed. So this is the one we have to be careful for abort also, because under abort condition we will not be following the nominal profile. So you will be somewhere and then suddenly you have to come back. So then under that condition, the accelerations due when the jerk, when it is experienced, that should not be too high. So these are the difficult or maybe slightly uncomfortable parts. But the very enjoyable part is, of course, getting into microgravity, because they all have something that mascot will suddenly start flying, and that is something very enjoyable. I wish we also could experience all that. And the second question, what was this second question, Bharadwaj?
Yeah, the second question was that what is the most important aspect for their health?
Right. Their
they are
health,
protecting?
health. Actually, if you're, we can probably split it into two parts. If you're thinking of a short duration flight and a long duration flight. For a short duration flight, this osteoporosis and those things are really not so important. But still, and even the muscle wastage also may not be very important, but still they are in microgravity. And the way their body react to microgravity, they it may not be always predictable. So cardiac health is extremely important, and that is something which is tested and also ensured. And that's why the regular fitness checks are required for somebody who is getting ready for space flight. That's one thing. The second one is the space motion sickness. That is something which is absolutely impossible to predict. Even people who may be having motion sickness on earth, they may not have. People who don't have may have. So all this is something which still is in the domain of partly the unknown. Even though the yoga studies show that there is some benefit, but we don't have enough samples to say whether it is really so as of now. I mean, later on, probably it will come. Thank you for those questions.
Thank you so much.
We have a question from Dr. Harish Gadavi. So, Dr. Gadavi, you can ask your question.
Hello, madam. Am I audible?
Yes, you are.
Yeah. Thank you for very wonderful talk. I have a question about this space travel. We are seeing a lot of companies are trying to come into the space travel. Space travel basically means that a person without training can actually also go to this thing. So, what are the technological challenges? I mean, is the technology already available and we have to put it together, or there is still a gap in technology that needs to be developed to be space travel to be real?
Now, here I would probably like to again distinguish between the two aspects of space travel. If you are only looking at somebody who is going as a tourist and then coming back and doesn't have an active role in space. That would be one kettle of fish. The other would be a real astronaut who has to actually go there, and they may have to do something. And so these are two different classes. One could be a tourist, but the other person, the real astronauts really have to be trained for any contingencies and for the task which they are supposed to perform while they are in orbit. I don't have any first-hand experience with respect to tourists, but we are all seeing that now a lot of people with physical challenges, young and old, they are going and they are coming back. But mostly most of them have been suborbital flights or short duration flights. Seem to be okay. There is some training that is imparted to them, but obviously that's a very short kind of training, maybe to make sure that they don't have any problems and they are prepared for what they encounter.
Oh, thank you, ma'am.
I'm not talking from our experience. This is only what I've seen.
Thank you.
Thank you.
So we have a question from Professor Varun Shi.
Yeah, thank you very much for a very comprehensive overview of the challenges in human space. Right? I have a related question in terms of sending these astronauts to space. What is the policy of India or ISRO? We would like to send civilians also to space, because there is some difference between civilians and normally, people in America also, they used to send first armed forces because they are better trained. So what would be the policy of ISRO to send such astronauts? Because civilians would require much more rigorous training compared to other people.
Thank you very much for the question. I will answer it. Before that, I would like to say that, okay, I'm not speaking on behalf of ISRO. I'm just telling as an individual. First of all, I've retired from ISRO, even otherwise. But I know that, see, we are, in the beginning, we are not planning. The first mission will obviously have trained pilots, which we all know. But later on, you know that what's going on right now. But later on, as we move into the sustained part of our program, definitely civilians will be there. There's no question of that. They will be there, and it is for the nation. It is not just for an elite group of people. Again, this is my own individual answer to the question, but I'm sure it is going to be like that only.
And
Yeah,
just
giving-
related,
So she is giving us hope. You can go.
I myself would like to go.
And just a very naive question, we used to see this series like Star Trek and, very early. So there they will show the ships, very comfortable. These people used to be very comfortable in the environment. So is this basically, will this still be a fiction in the coming years, or we will be able to achieve that kind of?
Oh, I'm sorry. I didn't catch the question. I couldn't hear it
See,
properly.
Yeah. So basically, when we send astronauts to space at present, they are not in a very comfortable environment, maybe because of the volume or because of the systems. But whenever we see, these fiction movies like Star Trek and all, there the spaceship have a very comfortable environment. So will we be able to reach that technology, or will it still remain a fiction?
Oh, I think I caught it partially. I think I was responding to Dr. Bhardwaj's question on which are the uncomfortable, but orbital flight is a very, very comfortable thing. Even if you are in a reasonably cramped environment, the reason is you have all the three dimensions to operate. There's no floor or roof, and you have the entire space which you can use, and the view outside is there, it is something which we can never see from Earth, and it is very comfortable. It is nothing to do with the technology, of course, there will be a lot of sound because all of the, and there are noise cancellation earphones which they can use, and attenuating the noise within the cabin. That is something which it is already partly successful, but I think much more work is being done on that. And as I already mentioned, the ergonomics will be designed. So the color scheme, the position of all the, like, they will be designed so that they have both the physical comfort as well as the psychological well-being. That will be taken care. I think that's what you were asking. Sorry, I could not catch the question fully.
Yes. Thank you. Thank you.
Thank you, madam. Next question is from Nirbhay Upadhyay from PRL. Nirbhay.
Yes, thank you, Durga. Thank you, madam, for giving this insightful lecture. I have two questions basically. Number one, actually, you have quoted two tests which are CARE mission and SRE and PEDABO test, three basically. So there basically we have tested this forward heat shield, which were actually different in SRE as well as in Gaganyaan set, formerly as HSP.
Right.
So whether these two experiments alone are sufficient to guarantee the human rating level which we target, one thing. This is question number one. The second question is this PEDABO test, which is related to crew escape safety. Whether we shouldn't have some more tests like that before going with actual manned mission, because you have not stated on the numbers of the unmanned flights, which are, I think, quite reduced from the original plan, which used to be discussed in the when it's HSP or in inception.
Thank you for the question. I would also like to mention that the number of tests, that will depend on the outcome of the first test in each case. And it is not that SRE and CARE are sufficient and we can go ahead. Absolutely not. But those are two experiments where we gained I did not actually, it's not the thermal aspect alone. We came from orbit. In SRE, we came from orbit, we splashed down and we recovered. So it is something where from orbital, and we splashed down where we wanted to splash down. That is some experience which otherwise we would never get, that is one. In CARE is not that kind of mission, but CARE really did not go to orbit because it was the first experimental mission of the GSLV Mark III. So there we had something that is very similar to the crew module which we have, and then that had come down and then braking and then splashed down. So I meant that segment alone, and obviously those are only like precursor experiments. There are a whole series of experiments which are charted out to test the specific subsystems, to test the systems, to test the various conditions of the mission profile, including the PADABOT. When PADABOT, that was just the first test. I showed it just to show the kind of crew escape system which we have, and that's so much more is to be done. Absolutely, I fully agree with you that I just said that this is the starting point. It's only the starting point. There's much more that needs to be done.
So sorry to add one more thing here, having listened from you that a series of testing will be there. So this timeline given, which was anyway declared by Honorable Prime Minister. So how in tandem with that we are in present situation?
No, again, I would not like to get too much into that because this is, again, I'm not speaking on behalf of ISRO right now. This is a general talk. There are obviously there will be some delays, but then there is a clear direction for moving forward. So I would not like to comment too much on that right now in this talk.
Thank you, ma'am. Thank you.
Thank you, madam. Shiv Kumar Goel from PRL wants to ask a question. Goel, please.
Ma'am, good evening. Thank you for giving some such excellent talk. I just had quick two questions. One of them was, you said that this crew module, as far as we have seen that usually there are 3 members in a crew module. So what is our plan and why only minimum 3 persons? I mean, what is the criteria of selecting at least 3 persons in a crew module? Or ISRO has different kind of people, or how many people are going to be in the crew module basically? And second question is regarding this technology which you are referring, like with that technology, the travel time, for example, to Mars can be reduced from months to days. So what is that technology and what is the status of that technology basically?
We don't have it now for a human space mission. We don't have it. But then it is the one of the promising technologies is going to come very soon. But the problem with the human mission, what I was trying to drive is that the humans have, one is the lifespan, and the second is the resources, isn't it? If you have a travel time of 1 year, so you have to carry all those resources with you, and you will be in an enclosed environment, maybe by yourself, maybe with 2 or 3 others. The psychological effects could be tremendous. I mean, even though they have had Martian analogs on Earth and they have done a lot of testing, but travel times even beyond 6 months, I do not know how it will impact on the team. It is one of the things that is yet to be addressed. So this is not that plasma travel and all is all for the future. It's not. So currently I was only trying to impress upon the audience why we are not in a position to travel far away from the Earth. So these are the things which are pulling us back.
Yeah. And the first question was regarding this number of people in the crew module.
Okay. So there, see, I can only say that, again, it boils down to the mass. I was already saying it depends on the number of crew, the duration of the mission, all have an impact on the mass which we have to carry to orbit. As of now, we have only one GSLV Mark III. So there is an upper limit. So you cannot have anything beyond that. So that decides the capability of the launch vehicle, and the mission decides the upper limit. So we go with the upper limit. So anything less than that will be possible.
Thank you, ma'am.
Yeah, we have a question now from Dr. Navinder Singh.
Yeah, thank you, madam. Thank you very much for this wonderful Amrit Vyakyan. We really enjoyed it. So my question is related to the thrust mechanisms. You mentioned about this plasma thrust mechanism. So now currently the technology is solid propellants. And what is the current stage of development of this plasma thrust system, and how does it work? Whether you have some sort of particles like protons which are accelerated within the two electrodes of opposite polarity, and then they are they are escaped, and could you please explain the mechanism?
No, I cannot go into details because I do not know the details myself, but definitely these are being used. Even the some of the small space probes are trying to use this in a very small way. That's why this is all to the future. One problem which we are likely to face is that when we are looking at a human space mission, even beyond the launch vehicle phase, we will still have a very heavy module.
Yeah.
And the problem with many of these, they are very efficient. They are extremely fuel efficient, but they may not be developing the kind of thrust which we need to push heavy payloads at present. But later on, this is one of the technologies which can help us. Otherwise we don't have many options which can take us to the outer reaches of the solar system. That is the truth right now. That's because we are not dealing with small systems. We are dealing with large systems.
That's right.
So we've not reached anywhere near that.
Okay, thank you, ma'am.
Dr. Vineet, you may ask your question.
Thank you very much, Dr. Lalitambika, for such a nice talk. And so I'm just curious to ask one thing, and I would like to know that it's not on the technicality, but the human aspect of sending the missions, like the longer missions to Mars. So generally people, they have to live in isolation, like, and we would like to have, like, meet more people, be more social, and generally it would be limited to interacting with only 3 people or 4 people. So in order to prepare for that, there means I think there would be some experiments being done where some people are kept in isolation for in somewhere on Earth. So how important these experiments are like they are in Earth somewhere, but how important these experiments are proven for preparing for these longer missions?
That is a very, very interesting question. And this is what I was just touching upon, that these analog missions which are there on Earth, they are extremely important because human beings tend to, there is a rapport which is to be built with the rest of the team. And conflict, it is very easy to develop conflict. And here there are no cues outside the cabin, you know. They can see only space, nothing, there's nothing else. So there could also be other requirements, like you may need to project some view of greenery or something inside to maintain their mental condition. Especially if they have to do a lot of uh, work, or if the workload is too high and they are facing some cognitive difficulties, then there is a possibility that they can either develop an interpersonal conflict, or they can develop some rebellious attitude to the ground, which had actually happened in one of the missions, isn't it? So such issues, we have to, that compatibility is very important. This happens even when selecting a team, and the compatibility should be not only within the team, it also has to be between the team of people who are going and the team of people who are supporting them on the ground. They have to work together. And there, of course, personality clashes can develop at any time, but this aspect becomes very important if you are going on a long mission and there's no other way out, you know, you all are trapped within and are together.
Okay, thank you very
So
much.
those are all really now also uncharted waters, I would say. To a certain extent only we have the answers to those questions.
Yeah, just a comment that means like I would relate, means we work in the field of oceanography, so we also have to go on cruises
Yeah.
like 30 days on the ship and with limited
Right.
number of people. So
Right.
I could relate to it, but of course the scale and magnitude is much larger here because less number of people and longer durations. So yeah, thank you very much for the wonderful answer.
Yeah, I would like to give one more comment. You know, you may not be able to come back because of the constraints of your mission in when you're in the ocean, but you can come back. You know,
Yes,
you
definitely.
can come back by yourself, theoretically at least.
Yes.
That's always there at the back of your mind. But
Yes.
whereas, where is the option? You are on a trip to Mars. The aborting the mission somewhere in the middle and coming back may happen only under some dire emergency. That means the entire mission is aborted. No one person can come back. Entire
Yeah.
team has to be come back. It will be a different frame of mind altogether. That's what I was trying to say.
Yes. Thank you very much for the wonderful answer.
Thank you, madam. Professor R.P. Singh wants to ask something.
Yeah, just one question. How our human space mission is different from design aspects from Virgin and SpaceX? Both have done this human space mission, Virgin as well as SpaceX. How our mission is different from them? Design aspects like launch, both are different.
Right.
SpaceX and Virgin, and how our is different from them?
Okay. No, I will tell you in a slightly different way, without directly comparing. We have built up our space program from ground up, increasing the capabilities. So we are looking at the launch capability first. So our launch vehicle is the best available launch vehicle for a human space mission is a GSLV Mark III. So first of all, the launch vehicle is also having its own characteristics, which is different from the Falcon or SpaceX or whatever. It's totally different. This is the one. The second one is that we are, ours is a short duration mission. Of course, theirs also is a short duration mission. No, there are many technical differences, like the way we come back, the landing. We can do it only on water. I mean, there's no option for us to come on land. So that is probably another difference. But I would say that the essence of the technical challenges which we need to overcome, which we have to do ourselves also. We cannot get this from anywhere else on a plate. Some information only we will get. We'll have to wet our hands and develop all the technology ourselves. I would say that the core of the technology which we need to master would be no different from the core of the technology which they have already mastered. It will be the same. But ours is our own program, and we are doing it from our launch station at Sriharikota. So the mission will be accordingly defined with our own launch vehicle and our own technology. So later on, we will be in a position probably to shake hands on equal terms with anybody else. That's the idea.
So just one more question. NASA came out after one disaster, this government agency. They came out of this human space missions. Okay, they used to send. And they have given it to private agencies now. They are doing these things. So, but our government is entering into this kind of space mission. Do you think it's advisable or it's not advisable? What is your comment?
No, it is. I fully agree with you that we have to make sure that the entire system is safe and the astronauts are safe. I mean, safety is paramount in a human space mission. Whoever does it, whether it is a government who does it or a private agency who does it, yes, that is one aspect that we definitely have to take care. But the other aspect is that in the space domain, there is a gap in the knowledge of our country, which needs to be bridged. That's first and foremost. Once we bridge the knowledge, then there are many opportunities will open up in other domains. Then we may decide to do it later on cooperatively, and all that is in the future. But there's a gap. There should not be a gap. The moment there is a gap, then we are vulnerable. This is my perception of this. Why we need to do it. Thank you.
Thank you.
Yeah, thank you very much, madam. So I don't see any further questions on WebEx panel, but still if anybody has, they can raise their hand. We'll take it up after taking the YouTube questions. So before going to the questions from participants who have joined on YouTube, I myself have one question. Actually, I have two questions which are interrelated. So as I understand the Gaganyaan program, there will be initially some test flights where there would be some dummy, and even I heard that there would be humanoid robots would be sent. So how many such missions would be there? And then before going with the actual human space program, space mission?
Yeah. Okay, actually, we cannot answer that question right now. That is, the practice is to have one mission, fully instrument it, then see whether there are any anomalies of any kind, then decide the further course of the program. That's how the only way it can be done, whenever we are embarking on something for the very first time. So we are at that position right now. So the number is not just to add confidence. In this case, it is also a learning process. The first one will definitely be a learning one. Lot of things we will learn. We have learned from all our first missions. We have learned so many things. That will still happen because there are a lot of unknowns.
So I have a follow-up
we
question.
can answer this question probably.
I have a follow-up question to this, man. So I heard that there would be at least one mission where a humanoid robot would be sent. So is it only for the safety aspects, or this will also help in studying the physical and mental health in some way? I don't say it can completely be mimicked, but in some way will it help?
Physical, yes. Physical, yes. Because, there will be a seat, and then the places where their body is touching, the various stresses that will come on various parts. To a certain extent, some of these things can be evaluated. It is, yeah.
Thank you very much, madam. Yeah. So we'll go to the questions by our participants who have joined on YouTube. The first question is that most of the capsules landing in water have some sort of post-landing stabilization. So what kind of post-landing stabilization will Gaganyaan have?
It will also have post-landing stabilization because as the questioner rightly put, that is something that is required because the recovery will not be immediate. It will take a little bit of time. So before that, the stabilization will be there. It will be some kind of flotation device which will be fitted. I mean, exactly how it is going to be, I cannot tell right now. There are many options, you know. It can, on its own, it can do, or somebody, some diver or somebody can come and fit, if they are in the vicinity. There are many different options that are possible, but definitely there will be such a device.
So the next question is from Aditya Sarda. Why we have decided to have an inclination of 51.5 degree for the human space program mission?
That is again another very good question. You know where we are launching from. You know, we are launching from India. So this inclination, for some other reasons, others would have chosen something similar to that, maybe. But in our case, it is defined by our mission requirements. Please bear in mind that I was saying that there should not be, that black zones have to be avoided, that we have an option of only landing on water, and we have to avoid all land masses during the ascent trajectory. So this is the prime consideration which has decided this. And don't take this 51.5 and all in the picture as sacrosanct. It may go 0.5 degree that side, or 0.5 degree this side, or maybe up to 1 degree this way, that way. Will final mission design time, this may change slightly, but not much.
Thank you, madam. The next question is from Dr. Nagrani. He want to know, we have done pad abort test, but what about in-flight abort?
That is again a very interesting question. I was mentioning a series of tests which need to be done, and in the ascent, the atmospheric ascent being very critical, there are certain specific regions of atmospheric ascent which are more critical. Like you have this high dynamic pressure regime, you have this transonic regime. So such places have to be tested. Definitely they have to be tested separately. So there will be some kind of vehicle, test vehicle, which will take this system to that condition, and then abort will be simulated, so that we must know whether the parachutes deploy properly, whether the orientation comes properly, and whether it gets recovered. So that is all there. All will be tested. It's a very good question, and it is planned also.
So there is a question about astronaut dosimetry, that is radiation dosimetry, from Professor D.
Yes.
Banerjee. So he wants to know whether it is being considered for human spaceflight program.
Yes, it is very much. Because we need to know. We need to know even before the humans get in about the what kind of radiation is going to be there, and when they are there, of course, it has to be there. It's planned.
So in your talk, you have talked about some adaptive structures. So Dr. Vaibhav Dikshit wants to know, and he wants you to just have a brief light on how adaptive structures work to reduce mass and its application in Gaganyaan mission.
Okay. Actually, I am not an expert on structures. I will, that disclaimer, but I will tell you how it will. Adaptive structures, you know that there will be certain parts of the structure which are heavily loaded, and normally what we do is we will strengthen those vulnerable parts. So if a structure is adaptable to a certain extent, those vulnerabilities, and the vulnerabilities may not be there all the time, you know, it will be there under certain conditions. So if a structure can adapt such that under those conditions more stiffness is provided, then the overall mass should certainly reduce. So this is not my domain fully, but this is the basic idea. Like smart structures, a lot of experimentation is going on there.
Thank you, madam. So there is
I would also like to add just one more on that. Like when we consider deployable structures, you know, it is even more than the mass, the volume comes down. So when we launch them, we will be launching them in folded condition. So the envelope of the launch vehicle which contains them need not be so large. And then later on we deploy, and then we get what we want from it. So there are many dimensions to how a structure which is a very versatile one can lead to mass reduction. Thank you.
Thank you, madam. There is one more question from Aditya Sarda. So the descending is planned at T0 plus 14-15 seconds. So do our spacecraft, the descending is planned at T0 plus 1415 seconds. So do our spacecraft would only be staying for 24 minutes in the orbit?
No. Descending is not planned at that time. Maybe that picture which I showed was showing like that. No, it will be after orbit. It will be continuing in orbit, and then there will be one more T naught probably from the time of deboost.
Okay.
So that is the next T naught. But I don't know which exactly.
Yeah, maybe that.
I must compliment her on very closely attending to the lecture. No, you don't go up and come back immediately. You be in orbit, but then the T itself will get reset, when your next operation starts.
So there are a few more questions. One question is from Dr. Rajkumar. How qualification of human spaceflight is different from satellite launch?
How qualification is different? Okay, actually, I was mentioning that safety is paramount, and this is applicable right from the component onwards. The reliability has to be much more. This is a very it merits a full lecture in itself. So from component selection onwards, and the industries which make the components, how they are addressing the kind of zero defect systems, how they are building up the subsystems, how we are ensuring at each and every level we are able to certify the product for a human mission. It's a process which is much more stringent than for an ordinary product, and this is one of the fringe benefits you get from embarking on a human space mission, because the whichever industries are catering to a human space mission, they have to be of the highest possible standards. I mean, there's no compromise allowed anywhere, and so it enhances the overall quality. I cannot answer more in this lecture because it is a big topic in itself.
So this is the last question from YouTube. So the question is about the lightning. What precautions are being taken against lightnings while traveling human space vehicle towards the space or planet?
Against lightning?
Against lightning.
Okay, all I can tell is that this precaution is not just for human space mission. It is there even for our satellite missions also. So this, especially when we are preparing for the launch, and we will have some advance notice whenever there's going to be lightning, and there are warnings like level 1, level 2, level 3. So depending on that, there will be some action that is taken to save the entire system so that there is no lightning hit. And at the launch pad, anyway, there are many elaborate systems which are in place so that there is no lightning hit. This is applicable not just for human space mission, it is applicable for all missions, because we are dealing with propellant systems which are there. Yes. Thank you for the question.
YouTube questions are complete. Now, actually, we have one question from our chairman of our Vyakyan committee, Professor Nandita Srivastava.
Yes.
So thank you, Dr. Lalitambika, for a very insightful talk. I had a small question. You mentioned that the spacesuit for the EVA, the extravehicular activity, is different from
Yes.
what we have in capsule, and it's almost like a mini spacecraft itself.
Yes.
So does it mean that there is a limit to the duration of the experiment that can be done outside the spacecraft? And if that is so, what limits it, and how much time has on an average spacewalk been done in the past?
Okay, I don't think I have the exact numbers, but I'll tell you what limits it. Because there is a portable life support system which is essential if you are outside, isn't it? You cannot draw upon the resources which are inside, and then that is one thing. So even though you have all the systems in place, your resources are limited, whatever resources you have. And I am not very sure about the maintenance of the partial pressure within the suit. Beyond a point, the proportion of carbon dioxide and oxygen, they may not be able to do anything, because in the cabin they can do the scrubbing and they can reduce the carbon dioxide level and maintain the partial pressure. That may not be possible. That's one thing. Then other than that, Okay, there is also a cooling system, but all this will have some time limits when you are outside. I don't really know exactly what is the time limit and how much time people have at most spent in EVA activities. I look it up right now. I don't know. It's a very good question, however. Thank you.
Thank you very much, madam, for patiently answering all the questions and elaborating on them. I don't see any further questions either from WebEx or YouTube. So I'll hand over it to Professor Lokesh Sahu for vote of thanks. Over to you, Professor Lokesh Sahu.
Just a minute. Even before that, I must say how much I enjoyed this interaction. So I really want to thank all of you, starting from Dr. Bharadwaj and all of you. Okay, please.
Thank you very much.
Thank you, Durga, and it is now my pleasant duty to formally conclude today's PRLCA Vakhyan session. First of all, we are very much thankful to Dr. Lalitambika for accepting our invitation to deliver Vakhyan on very interesting topic of human space program challenges and strategies. And we are very much thankful to our viewers who very enthusiastically, interacted with you and asked a lot of questions, rather curious questions, and make the session overall very, very exciting. So it is also an opportunity to thank all colleagues, the Vakhyan team, and particularly our director, Professor Anil Bharadwaj, Dean, who is not here today, Professor D. Pallam Raju, and Chair of the committee, Professor Anita Srivastava, for hosting this excellent Vakhyan. And also we are thankful to all our viewers for joining the celebrations of 75th years of independence, Azadi Ka Amrit Mahotsav, which is part of this, and this Vakhyan is part of that. And we have a lot of more lectures coming in, and we request our viewers to be in touch with us through our website and also through YouTube. And with this, I formally propose to close today's session. Thank you.
Thank you.
So let me also join my colleague, Professor Lokesh, to thank Dr. Lalitambika for a very excellent talk and very informative for many of us who are quite novice in these areas, which is highly technologically intensive in one aspect and human aspect which has to be taken into account in this kind of missions. So thank you, Lalitambika, for a very wonderful talk. And thanks to all the colleagues for interacting with her.
Thank you.
Thank you. Take